Okay, I think we're about to make a start. Welcome to Friday, everybody. It's the last day. It's a good job. As you can probably tell, I'm about to lose my voice, so hopefully I'll make it through the rest of today. Welcome to the Earthquake Early Warning session. There are actually 3 sessions today on this. The 2 oral sessions this morning. The first one this morning will be focused mostly on looking at experiences in Japan from the Tohoku earthquake. And then the second session in the same room at 10:20, we'll be looking at other ongoing efforts with earthquake early warning around the world. And then this afternoon, there's a poster session with a large number of posters talking about even more early warning. So I'd like to introduce my co-convener, Dr. Kenji Doi from JMA, and he's going to introduce the speakers.
Good morning, everyone. I'm Kenji Doi from Japan Meteorological Agency. So I would like to introduce the first speaker, Mitsuki Hoshiba, titled Performance of the JMA Earthquake Early Warning for the 2011 of the Pacific coast of Tohoku earthquake. So, please.
Thank you. Thank you very much for giving me the opportunity of the invited presentations. Today, I'd like to talk about the performance of JMA earthquake early warning for the 2011 of the Pacific coast of Tohoku earthquake. I will show the performance of JMA-EW for the magnitude 9 earthquake, functioned as expected and malfunctioned, and feedback from users and the general public, plus amplitude and frequency of the first 3 to 30 seconds from a technical point of view. First of all, would you hear this sound? Okay, so this is an uncomfortable sound, but it has an important meaning. The earthquake early warning in Japan. Probably Japanese audience know the meaning of it, but please keep secret. I will explain later. Okay. So this is a brief summary of JMA-EW. It was fully operational in October 2007, 4 years ago. It was service nationwide and issued to general public using TVs, radio, and cellular phone broadcasting mail. And magnitude determines the maximum amplitude of ongoing waveform. And the growth of the rupture is monitored using the amplitude in real-time manner. Anyways, in JMA, magnitude is not from the frequency constant. Magnitude is from determined maximum amplitude. And finally, it's a JMA-EW. This updated repeatedly as available data increases lapse time. For example, magnitude 9 earthquake, totally 15 EWs were issued from JMA. Here, I hope to explain the JMA seismic intensity scale. JMA seismic intensity scale is ranging from 0 to 7. Seismic intensity 0, JMA seismic intensity scale, which means only seismometer detects a seismic wave. And seismic intensity 1 means people barely felt the earthquake. And intensity 7 is the maximum limit. And seismic intensity 5 and seismic intensity 6 are divided by 2. So that is seismic intensity 6 upper, 6 lower, 5 upper, and 5 lowers. Totally 10 degrees. 10 degrees are used for representing a ground motion on the JMA seismic intensity scale. And so there is 2 grades. There are 2 grades for JMA-EW. One is called forecast, and the other is called warning. Forecast is in case seismic intensity 3 or larger are expected, or magnitude 3.5 or larger are expected. And this message is a region when seismic intensity 4 or larger are especially specified in the forecast message. And warning. Warning is a message for the region of seismic intensity 5L or larger. And so the grade forecast or warning, this is determined depending on seismic intensity, not magnitude. So for example, so warning, this boundary, seismic intensity 4 and seismic intensity 5L, this boundary is important for the JMA-EW for warning. And warning is broadcast by TV, radio, and cellular phone mail. So as you can imagine, the sound is this one, okay? The cellular phone. So which means that this cellular phone receives the earthquake early warning message. And one more important sound is this one. Okay, this is for TV and radio. In Japan, there's a lot of TV and radio company, more than 1,000, 100. But they commonly use this sound commonly. Okay, so I will explain the performance magnitude 9 earthquake. A lot of people are killed, most by tsunami, and a lot of people are even now missing. And so I will hear the performance of JMA-EEW for the magnitude 9 earthquake using the animations. So in the animations, pink, yellow. Yellow area means a forecast region, which means seismic intensity 4 is expected. And pink region means a warning region, which means a region seismic intensity 5L or larger are expected. And I will show the waveform observed at the host stations. And here, this is the lapse time from origin, lapse time from the first forecast, lapse time from the first warning. And as I told before, for this earthquake, totally 15 issue is issued. So this is the number of earthquake early warning number, and this is the magnitude estimated at the moment. Okay, so earthquake occurred, and P wave and S wave generated from the source. And then at the nearest station, P wave is detected. And this point, at the, you see, at the forecast issued, and then warning was issued. At the time, it's observed intensity is at most 2. And around here, seismic intensity 0, which means nobody felt the earthquake. And this is earlier than the S wave arrival. And then seismic intensity is expanding and expanding at Tohoku regions. And the forecast region is expanding and expanding according to the increase of the magnitude. Okay, so at the present, at the Tohoku region is a strong ground motion, and Fukushima region is from now on, it's a strong ground motion start at Fukushima regions. And this is a 12 assurance, magnitude estimated to be 7.9. And 30 assurance, magnitude estimated to be 8.0 something. And at present, it's a strong ground motion at Kanto area is from now on. It's no. And this is the final assurance is a 15 assurance, this timing. At the time is a Kanto area, it's strong motion is not yet. Strong motion Kanto area start from now. It's a strong ground motion expanding at Kanto areas. Okay, something like that. Okay, at the time it's NHK, the broadcasting, NHK is a public broadcasting TV. They broadcasted the discussion at the diet. So this is a
このような対応を講じまして、現緊急それから
緊急地震速報です。強い揺れに警戒してください。
Strong motion expected at 宮城、岩手、福島、秋田、山形 prefectures。
強い揺れに警戒してください。
現物給付の
Okay, this is the expectation of ground motions. Expectation of this is the earthquake early warning.
ですが、地震津波関連の情報をお伝えしま
So
す。
NHK changed the program to
東京のスタジオも
use.
揺れています。緊急地震速報が出ました。宮城県、岩手
So
県、
this
福
is the
島県、
expectation of
秋田
ground
県、
motion
山形
earthquake
県
early warning.
緊
This
急
is
地
the
震速報です。
observation.
また今
Observation of the
東京
ground
渋谷のスタ
motion.
ジオも揺れを感じています
2:46 p.m. at
東京渋谷
Tohoku
のスタジオ
region,
も揺れ
strong
てい
ground
ます。
motion was
強い
observed.
揺れを観測した地域の皆さんにお伝えします。
So this is the
落ち着いて
scene
行
of
動してくだ
Sendai.
さい。揺れが収まってから
Tohoku
火の
region,
始末をしてください。
seismic intensity 3 or larger are following
落ちてくる
regions.
ものや倒れてくるものから身を守ってください。現在東京渋谷のスタジオが大きく揺れています。東京渋谷のスタジオが大きく揺れています。東京の
So this is the
渋
scene
谷の
at
スタジオ
Tokyo.
が大きく揺れています。上から落ちてくるもの、倒れてくるものからまず身を守ってください。
So
揺れが収まるまで
2:46 p.m. Tohoku
しばら
region,
く安全な
strong
場所にい
ground
てくだ
motion
さ
were
い。
observed.
揺れが収まってから火の始末をしてください。
Pay much attention to tsunami at coastal line.
テレビやラジオのスイッチを切らないでください。午後2時46分の
Seismic intensity 3 or larger are observed at the following regions.
宮城県北部です。震度7が宮城
Seismic
県北
intensity
部。
7,
また
northern Miyagi
震度5弱
prefecture.
が山
Seismic
形県
intensity
震度
6
6
upper,
強が
central
宮城
Miyagi
県
and 福島 coastal
中部
line.
福島県浜通り、茨城県北部。震度6弱が岩手県沿岸南部、
6
岩手県内陸北部、
intensity 6 lower, 岩手 prefecture and southern Miyagi prefectures. And then this is a tsunami warning. This is a major tsunami warning and tsunami advisory.
海岸や川の河口付近には絶対に近づかないでください。
Video is very long, so I will skip here. So this is a snapshot of the animation. This is the timing as a warning plus 15 seconds, and warning plus 1 minute. When warning was issued, seismic intensity is at most 2 everywhere, and everywhere before than earlier than S wave arrival. Around here, nobody felt earthquake. And this is the timing of warning plus 50 seconds. So it took 50 seconds where seismic intensity 5L or larger were observed at the closest station to the epicenter, GIS stations. And this is the Tokyo region was specified in the forecast where seismic intensity 2 were observed at Tokyo. The timing is warning plus 1 minute. And so that was the performance of JMA-EW for the magnitude 9 earthquake. So I have to confess here that there are some malfunctions. One is the underestimation for Kanto regions. I explained that this is the timing of the final assurance, 50 assurance. At the time, forecast is issued at Kanto region, but warning is not, which means the seismic intensity 4 is expected. But actually, seismic intensity 5L or 6 upper were observed at Kanto region, which is due to the large extent of rupture of the magnitude 9 earthquake. And for the aftershocks, a lot of aftershocks, several aftershocks occurred simultaneously at a wide area, so system did not always determine hypocentral magnitude correctly, so which leads to overestimation of magnitude, overestimation of intensity, and then false alarm. So, for example, this is seismic activity. Okay, this is March 2, March 3. This is something like normal situations. March 5, March 6, March 7. At March 9 is a foreshock. March 9 foreshock, and then main shock, and a lot of aftershock. So several aftershock occurred simultaneously, which make a confusion of the JMA system. So this is an example of the wave propagation of the one earthquake fields, you see, and there are two wave front, so which means two earthquakes. So totally 3 earthquakes occurred simultaneously. In this case, system sometimes confused, which lead to the overestimation magnitude and then the false alarm. So how many forecasts and warning? So October 2007 and February 2011, totally 41 months. So for the warning, totally 17 warning was issued for 41 months, and one of them is a false alarm, but it's a software ban. In March, in April, 45, 60, 26, which means almost every day warning was issued. And then this number is a false alarm. False alarm means in this case, seismic intensity 3 or larger were not observed. So this is feedback from users. This is an article from Asahi Shimbun. Asahi Shimbun is one of the major newspaper company. This is the article of June 4. This is a questionnaire to cellular phone users after the magnitude 9 earthquake. Answer was from 1,200 people. There are some questions for a cellular phone. And question 3, which function is useful in your cellular phone? Number 1 is the cellular phone mail, probably. Number 2 is the earthquake early warning. Number 3, cellular phone, Twitter, blog, something. But anyway, earthquake early warning is second. So a lot of people think the earthquake early warning is useful. The sound is useful, even though there are some false alarm. Okay? So which encouraged me a lot, and it encouraged JMA, and it encouraged a community of EW, all of us here, I think so. So I show here the amplitude and frequency of the first several seconds from technical point of view. The amplitude of the magnitude 9 earthquake is very, very, very small, smaller than magnitude 6 event. Okay, acceleration also, the displacement also. The first several seconds, amplitude of the magnitude 9 earthquake is very, very, very small. Okay, so this is the first 3 seconds, acceleration, velocity, displacement. I analyzed the 4 earthquakes observed at the 4 stations. Okay, so magnitude 9 earthquake is smaller than magnitude 6 events. And then tau C. Tau C has a no clear dependence versus magnitude. And this is 3 seconds. So this is the first rupture is quite small. And the 3 second case, 4 seconds, 5, 10, 20, 30 seconds. Okay, the acceleration becomes larger than a magnitude 7 event at lapse times 20. And velocity and displacement at 30 seconds. But tau C is even now, even 30 seconds smaller than the magnitude 7 event. This is because it's a frequency contents of the magnitude 9 earthquake. So this is a spectrum of the first 30 seconds. The spectrum is very flat, no Fmax. So which means the magnitude 9 earthquake generates strong high frequency more than 10 hertz, more than 10 hertz. This is contrary to a lot of image of many cases. So this is the reason of the small tau C estimated for the magnitude 9 earthquake. Okay, so I will go to summary. So JMA either functioned as expected, but it was not completely perfect because underestimation of the Kanto regions, and for aftershock, JMA system did not always determine the hypotential magnitude correctly, which leads to some false alarm. Okay, finally, when you come to Japan and hear this sound, okay, this sound, I strongly recommend you take safety measure against strong ground shaking for your safety. Okay? Okay, thank you very much for your attention.
Thank you, Hoshiba-san. I have to ask you to leave some comments or questions, but time is almost over. So if you have any questions, short questions, I ask you. Okay, could you proceed to your microphone?
So you showed data from the nearest station, which was, of course, 100 kilometers away or 70 kilometers away. Is there any data from an OBS station that would be nearer, and could you show how the tau P and the other earthquake early warning values behaved close to the epicenter?
For this earthquake?
For the main shock.
For the main shock, there is no... we don't have a strong for the OBS, so there is no around Tohoku regions. So we don't use OBS around the Tohoku regions for an earthquake early warning. So it's the closest station that's the island for this case.
Thank you very much. And next speaker, I would like to introduce Mr. Masumi Yamada, titled Future Development for the Earthquake Early Warning System Following the 2011 off the Pacific Coast of Tohoku earthquake.
Okay, thank you. Hoshiba-san gave a really nice overview for the performance of the Japanese early warning system for the Tohoku earthquake. And I would like to share some stories how this early warning system contributed to the damage mitigation of Tohoku earthquake. Okay, this picture shows the damage of the Tohoku Shinkansen. This is a Japanese bullet train. And look at this, damage of the column. The strong shaking caused significant damage to this train. And this damage includes the damage of the cable column and cable itself, and this column of the structure, and also the rail track. And on March 11th, there are 27 bullet trains are running in Tohoku area. But this Tohoku bullet train installed the earthquake early warning system to control trains. So those 27 bullet trains running in Tohoku area, even though the structure caused such a significant damage, there are no derailments of the train, so which is one good thing. Okay, another example is early warning saved a worker near Fukushima. This person was working on this, he's painting the bridge on this top of this track. And then he received earthquake early warning by his cell phone. And immediately he recognized this is really strong shaking is coming. And he went down to the ground and told everyone working over there are strong earthquake is coming. And these are pictures this worker actually took at his place. And not only strong shaking, huge tsunami also came to his place. And this is a bridge he was painting. But fortunately, because he received earthquake early warning from his cell phone, so those people working here were able to evacuate safely. And there are good things and also bad things. This Tohoku earthquake revealed significant potential problem in the current JMA earthquake early warning system. One of the problems is large rupture dimension. Because the current JMA system uses point source estimation, they do not consider the fault rupture finiteness. So this is a distribution of the predicted intensity. And this figure shows the actual observed intensity. And you can see the big difference, especially south part of around here, And difference of the color indicates underestimation of the ground motion. And another problem is there are continuous aftershock, many aftershocks at the same time. So this one is also, Hoshiba-san also showed this figure, but before the Tohoku earthquake, there are many early warning issued, but the false alarm is about 20%. Here, like definition, false alarm is the difference of the intensity is greater than 2. And after the Tohoku event, there are much more than 3 times warnings, and the false alarm is more than 60%. And most of the reason is because multiple events, many events occurred at the same time. This is because there is a failure of hypocenter determination. The left map is showing this is a determination for the main shock, because main shock was separated events. So the hypocenter determination was pretty easy, and the error is pretty small. However, for aftershocks in the right figure, you can see very large error here, because aftershocks, there are many events at the same time, and also the contamination of the surface wave, and so that it's difficult to determine the hypocenter pretty accurately. And this is one example, 2 events occurred at the same time. First, one event occurs here, A, and then second event occurs here. Let me show you this movie again. So just be careful. First one is pretty quick, and second one's here. Now, event starts from A right now, and then now starting from B. So these 2 events occurred pretty close each other. And the magnitude of these 2 events is 2.5 for the first event, and second event 3.3. And JMA earthquake early warning said this is magnitude 5.9 event, which is totally overestimated. So this is what we have to do is possible solution for this, mislocation is look at this figure and assume this is all, seismic stations, and let one detects pretty strong shaking. And how you can classify these events? Because we are smart enough, we can tell events are here, just 2 events here, like this. However, computer is difficult because the current system uses a point source. So first, we need to locate the location of the first event, and the computer determines the location here. And later on, this station observed pretty large amplitude. And the current system, considers, there are pretty large amplitude far away from the source. So that means this is really large earthquake, and they give the warning. So what we have to do is we need to emulate human capability for judgments to classify multiple events. So we are going to introduce this particle filtering, which is a sequential Monte Carlo method. This is probabilistic approach instead of the deterministic approach in the current JMA system. And inside the particle filter, there are many particles, and each particle contains 5 parameters to estimate. So one, longitude and latitude, depth, these are location of the earthquake, and also the magnitude and origin time. So each particle contains these 5 parameters, and also based on 5 parameters, we can compute the importance of each particle. And first iteration, we sample particles in the 5-dimensional parameter space and compute the importance of each particle. And based on that importance probability, we resample the particle again, and we just continue this iteration until the particle converges to the final answer. And at the very end, the particle converges like this to the most probable parameter sets. And how to compute the importance of each particle. And we are going to introduce the log normal likelihood, which the difference between the observed displacement amplitude and estimated displacement amplitude. And estimated displacement amplitude is this equation. This is a function of location of the earthquake and also magnitude. So these are exactly same as CAD and JMA method, so I'm going to skip this equation. And I'm going to show you the performance of this particle filtering. Like this is exactly same example I showed the 2 events, small like magnitude 3 events at the same time. And let me show you the particles. First particle distributed here and converged quickly here. And second event was detected here and the particle like distributed like this and then converged pretty quickly. Let me show it again. Here, first event around here and converged very quickly, and second event detected here and converged quickly. Okay, so this is a time history of this 5 parameter, estimated 5 parameters. And blue one is showing the first event, and green one was showing the green line shows the second event. And left top one was the estimation of the magnitude. And this is a final answer in JMA catalog, seismic catalog. And look at the magnitude estimation here. The second event magnitude is really accurate. But the first one, you can see it's a little bit underestimated. But still, like you can see 2 events separately. And also, like this is a location estimation, and this is a catalog, and this dot is our estimated parameters. And you can see this is also pretty good. Like you can, at least you can classify 2 events without magnitude overestimation. And let me show you second example. This is just exactly same method, but just different earthquake. This is 2 events, actually here and here, and magnitude is 3.0 and 4.3. And the JMA estimated magnitude was 7.6, which is totally overestimated. And let me show you the performance of our approach. And first event detected here, and second event converged really quickly, but first event slowly moving like this way. Because the first one was offshore earthquake, so it's still a little bit takes for a while to converge to the final solution. And again, this is estimated parameters in time series. And you can see magnitude is pretty close to the final answer. And also, like the most important thing is we can classify 2 events like this. So first event moving like this way, and second event converged really quickly. So in this presentation, I focus on the second problem, a continuous solution for the continuous aftershocks. And we are still working on this particle filtering approach. But the couple of examples I showed here shows pretty good performance to classify multiple events. Thank you.
Thank you very much. Any questions, comments? Okay.
Good morning, Masumi. You showed how the events converge very nicely for 2 separate events, but how do they do for a single big event?
Single big events. I actually have the single big events to the next slide. So this is a main shock, okay? It's performance for the main shock. So it's converged here and then approached to the final solution. Slowly. So still, like, if it's 1 event, this method can tell this is just 1 event. And this is again this is a magnitude approach to the final solution, like this in time, and everything is okay. Yeah.
Okay. Could you proceed with your microphone?
How much computer time does it take? How fast is it on the computer? Is it Is it
It
efficient?
doesn't require a really long time. This is just using the personal computer, but still, it converts pretty quickly. It's just, the equation is really simple.
So it's just easy to run
Yeah.
with standard
Yes.
equipment?
Yeah.
Okay, thank you, Masumi. And I would like to introduce next speaker, Noda-san, titled Improvement of the Epicenter Estimation in Real Time by Using Single Station Data.
Thank you, Chairman. My presentation title is Improvement of Epicenter Estimation in Real Time by Using Single Station Data. The single station method, in other words, on-site method, by which epicenter location and magnitude are estimated from single station data, is in use for the present Japanese earthquake early warning systems, such as Japan Meteorological Agency system and the Shinkansen system. In particular, Shinkansen system use only single station method, don't use multi-station method, so it is important. In this method, epicenter locations are estimated from combination of the two kinds of algorithms. The first one is principal component analysis, PCA. This method is that back azimuth is determined by the first principal component of the particle motion for the initial P wave. This figure shows estimation of back azimuth by using the PCA. The first principal component equals to the direction with the minimum variance for the points of observed displacement. And the other one is B-delta method. This method is that the epicentral distance delta is determined by a coefficient B of the fitting function, like this function, applied to the initial P wave envelope. This figure shows estimation of epicentral distance by using the B-delta method. The coefficient B has high negative correlation with epicentral distance. Recently, Yamamoto et al. Proposed another method which applies the simple function CT to shorter data instead of the B-delta method. This figure shows estimation of epicentral distance by using the C-delta method. From this two methods, epicentral distance can be estimated more rapidly and accurately compared with the B-delta method. It is obvious that the coefficients B and C represent increasing rate of amplitude of the initial P wave. In this study, we propose new techniques to improve the estimation accuracy of back azimuth and epicentral distance in the single station method. At first, we suggest a new approach by using variable length time window in the estimation of back azimuth. In the next, we suggest a new relation equation between the coefficient B or C and the delta in the estimation of epicentral distance. Wave-home data observed at KNet operated by NID is used in the analysis of this study. Okay, at first, I will show you improvement in accuracy of back azimuth estimation. In the estimation, back azimuth is the analytical steps of the conventional approach as like this. Arrival time is calculated from the observed acceleration by the STA-LTM method, and displacement data is calculated from the observed acceleration records by using IIR filter, and the displacement data is bandpassed for 1 to 2 Hz by using IIR filter, and the back azimuth is determined from the PCA. Important point is that the length of the time window is fixed for all data in the PCA. In the present EW system, the length of the time window is basically said to be 1.1 second. This figure shows RMS of the estimation errors in case that the fixed time window whose lengths varied from 0.1 to 2.0 seconds by 0.1 second. In this case, error means absolute value of difference between the estimated back azimuth and the one published by JMA data set is like this. When the length of fixed time window is said to be 0.6 seconds, this point, the RMS is found to be the minimum. In other words, almost minimum in case that the 0.4 to 0.6 seconds is used. The RMS gets larger with the longer time window, like this, excluding the extremely short time window, like this. This figure shows example of the frequency of the errors estimated from the fixed time window. Left-hand side A and right-hand side B shows the results when 1.1 second and 0.6 second are used as the length of time window respectively. When 1.1 second is used as a time window, data whose error ranges between 160 and 180 degrees are relatively frequent, like this, compared with data whose error ranges between 60 and 160 degrees. However, such result is not obtained when 0.6 second is used, like this. So we consider that P waves with longer time windows are more largely contaminated by trailing scattered waves, and misjudges of the polarity of the initial P wave are often made when the longer time window are used. So in order to reduce the influence of the trailing scattered waves more effectively, we propose a variable time window approach. This figure shows the comparison between the conventional fixed time window and the new variable time window. In this new approach, the length from P wave onset, this point, to first zero cross point, this point, of UD component of the bandpass displacement data is adapted as the time window. So the important point of this new approach is that the length of time window vary according to the characteristic of each data. This figure shows frequency of the length of variable time window for each data. This figure shows comparison between the RMS by using the fixed time window, this figure, and the one by using the variable time window. This point is variable time window. The variable time window improves approximately 14% in accuracy compared with the result by using the fixed 0.6 second time window, which is the most accurate in case of the fixed time window. So we consider the new approach suggested in this study is very effective to estimate backagemass. Next, I will show you the improvement in accuracy of epicentral distance estimation. In the estimation of epicentral distance, the analytical steps of conventional method are as follows. Acceleration data is bandpassed for this band by using IR filter. The coefficient B or C is calculated from fitting function, like this, to initial P wave envelope respectively. And the epicentral distance is estimated from the coefficient B or C, which are negatively correlated with epicentral distance. This figure shows relationship between the coefficient B, left-hand side, and the coefficient C, right-hand side, and epicentral distance. Data set is like this. In the conventional method, relationship between B or C and epicentral distance is expressed like this. These equations take account of only geometrical attenuation. I mean, the first term of this equation is represent only geometrical attenuation. However, since the coefficient B or C have high correlation with amplitude, it is more natural to take also viscous attenuation into account. Therefore, we propose that the following equations to express the relationship between B or C and delta. The first and second term of right side of these equations indicate geometrical attenuation and viscous attenuation, respectively. In order to compare the conventional equation 1 with the proposed equation 2, in the last slide, the constant values are calculated by regression analysis. In the regression analysis, data are selected according to Fukushima and Tanaka in order to avoid the problem due to SN ratio. Number of waveform data is decreased to about 8,000. This figure shows comparison the regression lines by using the equation 1, which is conventional equation, with the equation 2, which is a new equation. The solid line represent conventional line, and dotted line represent new line. And we calculated the RMS of estimation error in logarithmic between the estimated delta and by using the equation 1, which is conventional one, and the 2, which is new one, shown in last figure, and the true delta calculated from the published JMA data. In case of data in which data is less than 100 kilometer, the RMS by using equation 2 almost equals to the one by using the equation 1, like this. So on the other hand, the RMS by using the equation 2 is improved approximately 10 to 15% compared with the one by using the equation 1. In case of the data in which delta is more than 100 kilometers. As a result, the RMS by using the equation 2 is improved approximately 7 to 9%. In general, the further is epicentral distance is the greater the effect of viscous attenuation relatively is. So the result obtained in this study exactly reflects this phenomenon. The improvement in accuracy by using the new relation equation is more remarkable the region where is far from hypocenter. This fact is very important for the event which occur at the shallower subduction zones. So we consider it's more appropriate that the new relation equation taking account not only geometrical attenuation but also viscous attenuation is used. And in case of estimation of epicentral distance by using the B delta and C delta method, because the new equation is not only physically more reasonable but also very effective to improve the accuracy. So my conclusion is like this. That's all. Thank you.
Thank you very much. We have 1 more minute. Any question or comments?
Thanks for the presentation, and I have 2 questions. One is that in your B delta method, and the fitting equation has 2 parameters. One is A and one is B. So B is related to the epicentral distance. So what about A? Does it have any physical meanings? And the second question is that you use a variable time window. So I didn't get how do you determine the variable time window? Thank you.
Your first question is this method. B indicate epicentral distance. A represent almost magnitude, but accuracy is not so good. And your second question is variable time window. First zero cross point is easily calculated in real time. I mean, the first point changes plus to minus or minus to plus of amplitude. Okay.
Zero cross. It's the zero cross.
Yes, zero cross point.
Okay. Thank you, Noda-san. And next speaker is Dr. Professor Andrew Zolo from Italy, titled "Early Warning for the Large Magnitude Earthquakes." Is it feasible?
Thank you. So I will present a retrospective analysis of the early warning parameters, the period parameter, and the peak displacement for the M9 Tohoku earthquake. We will first look at the effect of high pass filtering and width of the P-wave time window to be considered for the analysis. Then we look at evolutionary estimation of the two parameters and came up with the magnitude saturation. Then we move at further stations and we have the evidence for a two-step magnitude increase. And finally, I will discuss the possibility to have a rapid assessment of the potential damage for this event. How can I go? How can I move? How can we move the next? Okay. So these events provide a really important opportunity for studying these kind of things because of the very wide distribution of the strong motion stations from the Japan array, either on the distance and the azimuth. Here we see on the left the bandpass filtered sections of the waveforms for the vertical component of the displacement. So next, the parameters we are going to discuss are the period parameter tau c, which is well known in literature, then the initial displacement, which is measured in a given time window, and this parameter here is a proxy for the final pre-ground acceleration. There are a number of relationships which have been obtained by empirical regression of this data came from different regions of the world, and the general condition of using these parameters for early warning are displayed here. So we have generally very short time windows. We look at the vertical component, and the maximum range of distance is below 60 kilometers, and a high pass filter of 0.075 hertz. So when moving to the Tohoku case, we have necessarily to expand this kind of conditions. No, I'm not able. How can I move? How can I move forward? Forward. Okay. Okay. So the high-pass filtering is a critical issue because we need to correct in real time long-period artifacts due to the double integration of strong motion and to correct baseline. So what we did here is to make a combination study varying the cutoff frequency and the P-wave time window, and we came out with these conclusions that when we enlarge the time window and lower the cutoff frequency, we get higher values of PD and TOC. but logarithm of the two quantities scale almost linearly with the cutoff frequency for each considered time window. So the conclusion is that for each value of high pass cutoff frequency, the resulting logarithm of tau c and PD can be used for estimating the magnitude, provided that the proper scaling coefficients are obtained from the data. That's why we continue to use the 0.075 cutoff frequency for our analysis. So here I show the effect of enlarging the p-wave time windows at different p-wave time windows as for the two parameters. We have at the top the period parameter, then the PD, and then here we plot the prediction error, which represents the consistency between the predicted PGV and observed PGV. As you see from the very short time window, we have a big underestimation of the TOC corresponding to the events and the quite scattered distribution of PD. But as we move to larger time windows, this is for 15 seconds and then finally to 25 seconds, we get a stable TOC as a function of the distance, a decay of PD with distance, and a fairly good consistency between the predicted PGV and observed PGV. So let's look at more detail at the evolution of these two parameters with time, including the errors associated to the measurements. And these errors are due to the fact that we use many stations at any time to compute these parameters. So what we see is that globally, moving from short time windows to large time windows, we have an increase of the two parameters with a saturation appear around 20-25 seconds. And both parameters provide values which underestimate the final magnitude, although for the tau c we get a rather larger value than relative than for PD. We explain this discrepancy as an appropriate, not appropriate distance correction for the PD. But we know that we get, using this kind of window and the distance of stations, we get this estimation at 50 seconds after the first P-wave detection at the coastal stations. So we try to see, since the problem of the time window is crucial here, if going farther at a station where we could have the total P-wave arrival in, we could see which is the variation of those parameters. This is the case of station NG and H14, 540 kilometers away. And what we clearly see from this station is that a step increase in the tau c appear at later times, let's say 40-45 seconds, with the values, with final values which approximate the right value of the earthquake. And here we have the source time function which has been obtained using near source data on the top and teleseismic data, and we can see that it may be some correspondence from the two steps appearing in the tau c versus P-wave time window curve related to the occurrence of the two main episodes of the rupture. So the question here is, are these changes in this parameter correlated with the main moment episode release of the earthquakes? And could we use the measurement of these parameters as a function of the distance, as a function of the enlarged P-wave time window to track, in fact, the moment release of a large earthquake? So to conclude, I will discuss the possibility of getting a rapid assessment of the potential damage zone here we use a methodology that it's under publication on BSSA, where we obtain the shape of the potential damage zone by using observed PD values and interpolated PD values. And the theoretical values of PD are obtained by using an empirical relationship which uses both distance and TOSI estimations. And on this side, you see the intensity map as computed from the PGV, and you may see that at least for the central part of the investigator region, you have a good correspondence between the rapidly predicted potential damage zone and the observed intensity distribution, while this is not the case for the southern western part. And as already mentioned by Dr. Oshiba in his previous talk, and if you look at the data, you realize that in fact in this area the PGV is carried on by late phases, and probably just 25 seconds of the P-wave time window does not account for the arrival of late phases in this area here. So my final remarks here are the following. We have investigated the use of an evolutionary approach for fast magnitude estimation of a large earthquake by measuring two early warning parameters, a period parameter and a peak displacement, by gradually increasing the time windows after the P arrival. So if you use P-wave time windows smaller than 30 seconds, we see that both parameters show an increase and then stabilizes at some value which corresponded to magnitude 8.7 and magnitude 8. So the idea coming from this study is that we probably have to use some evolutionary estimation of the final magnitude by increasing the time window on the P wave. If we consider data from a farther station, we see that actually the TOC parameters still increase and get values which are close to the last one. But I have to say that we just did this analysis for one station, so it's not really statistically significant. We should test it on a much larger number of the stations. And if this is confirmed, it means that we should go farther for the early warning of large earthquakes, go farther at farther distances and looking at larger P-wave time windows. We argue that variation of the TOC may be associated to the two main rupture episodes of the Tohoku earthquakes. And finally, we see a good consistency of the potential damage zone as estimated by PD within a time window of 24 seconds. I know that the initial underestimation of the final magnitude by TOC does not seem to influence significantly the prediction of peak ground velocity. So maybe that for assessment of the damage through intensity of peak ground velocity, we really don't need to have a good magnitude estimation. Finally, this study has a difficult implementation in practice because we have to face with automatic selection of the proper time window, the problem of decreasing the signal-to-noise level as a function of distance. So this is a matter of future studies. Thank you very much.
Thank you very much. Any questions, comment for the? Could you use the microphone?
I can speak one way. You mentioned damage zone, but not building properties. Or did I miss it?
No. Actually,
if you have building properties, you cannot estimate the damage zone.
No. Actually, we talk damage, but in fact, the quantity we are talking here is the instrumental intensity, which is derived from peak ground velocity. So we don't, I don't now discuss how accurate are these relationship between the damages and these ground motion quantities.
Thank you, and I have a question. And I think the second point is by considering data from a further station at 440 kilometers and enlarging the P-wave time window to 70 seconds. And I just roughly calculated the arrival time of P-wave and S-wave, and it seems there's a time difference between P-wave and S-wave is around 50 seconds.
65.
Yeah, so the second, you mentioned there's a second increase when you estimated tau C. And so, I mean, is it because the arrival of S wave at the time, at the 40 or 50 seconds?
We estimated the arrival of S waves for this case using a travel time computation at 65 seconds. So we are well before the arrival of S wave. In fact, in all this analysis, I didn't mention, but we were careful taking away from the plotting all the data where the expected S waves could contribute, because we see clearly that when S waves are included in the analysis, parameters change because of the S wave. So in this case, I don't think at 40 seconds, 45 seconds, you have S wave arrival.
Okay, thank you.
Thank you very much again. The next speaker is Shiba-san again. The title is Expectation of Ground Motion in Earthquake Early Warning Using Real-Time Monitoring of Wave Field, a method based on the Kirchhoff-Fresnel integration without information of hypercenter and magnitude.
Okay, thank you very much. So, our title is Expectation of Ground Motion in Earthquake Early Warning Using Real-Time Monitoring of Wave Field. This is a method based on Kirchhoff-Fresnel integration without information of hypercenter and magnitude. So I would proposed here the method for expectation of ground motion using the quite dense station of seismic network. So for example, in Japan, it's a strong ground motion network. For example, it's a JMA network, JMA intensity network, local government network, KNet and KICnet of need have already equipped a potential for real-time observation of strong ground motions. So probably totally more than several thousand stations have already equipped or not yet potential of the real-time monitoring. So I'm here to aiming at the utilize the merit of the dense station for wave expectations. So I'm clarifying here the object of earthquake warning is expectation of ground motion, not rapid estimation of hypocentral magnitude. Hypocentral magnitude are method for expectation of ground motion. So I'm a basic situations. So what we experienced at Tohoku earthquake, so I explained in the first presentation, there's two more functions. One is the under expectation of the intensity due to the large extent of rupture. On the counter regions, GMS system expected seismic intensity 4, but actually observed 6 upper and 6 lower around here. So this is because due to large extent of the magnitude 9 earthquake. And also the multiple aftershock occurred simultaneously, so which make a confusion with the JMS system. JMS system did not always determine the hypocentral magnitude correctly, which leads to some false alarm. Okay, the example of something like that is I already show there's one earthquake around here, and then around here another earthquake occurred. Okay, so there's two earthquake occurred here. And more example, this is a one earthquake around here, you see, and then more larger one is from Pacific Oceans. So there's the two earthquakes occurred simultaneously. So in this case, system confused for the determination of potential and magnitude. But but looking at this real-time monitoring carefully in real time, which enable us to expect ground motion, even when we don't know hypocentral magnitude. So looking at this real-time monitoring carefully, we can enable to expect ground motion. So this is at present GMA method, for example, is using the observed waveform, and they first determine the hypocentral magnitude, which means identification of the causes, and then expectation of ground motion, which means the expectation of the on the causes. So I proposed here the method from observed seismic wave to directly to expectation of ground motion. This is the expectation of ground motion based on wave propagations. The image like that is from several seconds before. At present, we look at real-time monitoring, and then using this information to expect several seconds later. So this is observation ground motion to future ground motion. So the expectation of the ground motion, there is for example, there is 3 cases. There are target station, same distance, same amplitude observed. This case is something like a point source. This is a wave front is curved, wave front is a plane. In this case, we know that this case is expected amplitude is largest, this is second, this is smallest. So this relation is expressed in the following wave equations: Kirchhoff integral on a representation theorem on a high frequency approximation, Kirchhoff-Huygens-Fresnel integrals. So according to these relations, when we obtain observation of the on the shell S and wave propagation direction, we can exactly expect the ground motion at P. So in this case, so what happens outside S is included in the expectation automatically. So effect of source rupture extent on the directivity or simultaneous multiple sources are easily taken into account this method. Okay, so there is a concept of time for expectation of ground motion in this method. There is a source and target stations. So relatively near station, which corresponds to small shell S. In this case, precise expectation is possible, but warning time is short. Relatively far station from target station, which corresponds to a large shell S. In this case, long warning time, but expectation is not so precise. So relatively near station from target, warning time is short, but preciseness is good. Relatively far station, warning time is long, but precisely not so good. This is corresponding to the expectation of near futures, and this corresponding to expectation of distant future. Okay, so this is a relation which influences the ground motions, comparison with the method with magnitude. There is a source and target station. The path length A minus path length B is less than a half wave length, which means these relations. This region is important for ground motion at P. So for example, it's S wave, 3 km per s, and 1 hertz, and totally 100 km. In this case, these are approximately 10 km. So we know that about 10 km or 20 km, anyway, around here, we know very well about here. We don't know about 50 km, 100 km. We don't need these information. We know, if we know very well about here, it is enough for expectation of the ground motion here. So comparison with the magnitude. So for example, the target station here is Tokyo. So in this case, the wave coming to me is important for the ground motion. Wave going to this direction is not so important. So determination of magnitude, which means the same weight for all direction. So it is necessary to include the wave propagation into opposite direction? My answer is no. Anyway, wave propagating to me, that is important. If you know very well about this wave here and here, this is enough. We don't need to consider this waveform propagating this direction. So this is an example of the expectation of ground motion in case distance from source is much, much larger than the distance from distance between stations, which means geometric spreading factor, the correction of geometric spreading factor, is not required. So in this case, this formula become much simpler after assuming a far source and incidental angle from theta equals 0, which means vertical incident. I imagine here the borehole. So this waveform become this one, which means ground motion after the correction of the travel time, same ground motion is observed. Of course, in practice in seismology, we need a site correction. But after the correction of the travel time and site amplification factor, we can expect the ground motion at here. So I calculated that in case of the borehole, there is a case of the borehole at Tokyo Koto need stations, kicknet stations. The borehole is 3,000 meters. In this case, this is a real observation at the borehole in JMA intensities. And in this borehole, site factor is about 1.8 in the JMA scale, so 1.8 is added here. So this is the expectations. And blue is the real observations. So in this case, real-time monitoring at borehole at the depth of 3,000 meters, in this case, S-wave arrives 3 seconds before at borehole, so which enable us to expect ground motion 3 seconds before. And in case it's a geometrical spreading factor is required, in this case, we solve this according to the relations. For example, I calculated using the example of Tohoku earthquake. The green function, I used the delta function in the simple case. And it's a waveform. Depth dependence is assumed. So in this case, I assume independence of depth. And 1 Hz wave is assumed. Envelope is given by an observation. Using these assumptions, I calculated the expectation. This is a case of the target station to Tokyo. These stations using these front detections. So using this integral and using this assumption, red line is the expectations, red line expectation, and blue line is the real observation. So in this case, 50 to 17 kilometers apart. In this case, 15 seconds in advance. And this case is 30 to 50 seconds. In this case, 9 seconds in advance. And so this is in case of the 3 seconds. For the warning time, 3 seconds is enough. In this case, I think the borehole is very reliable. And you need, in case, 10 seconds. In this case, more deep borehole is not realistic, so we have to expand it horizontally. So for horizontally 10 seconds for the 10 seconds, we need about up to 30 to 40 kilometers from the target stations. And in case you need 20 seconds or something, in this case, geometrical spreading factor is required. In this case, 70 to 90 kilometers apart, the station, the information of this station are used for the expectation. So anyway, in this case, is expected near future, and this case is corresponding to distant futures. So this is a comparison with the present method. This is from hypocentral magnitude. At the Tohoku earthquake, 6 seconds from origin time, JMA system estimated to be magnitude 7.7. Using this information, ground motion is expected something. Spatial distribution waveform is something like that. Using this spatial distribution, this is corresponding to the current method. And but we have real observations. Real observation. So replacing with a real observation, and we make something like that, and then going to expectation of ground motion. This is my proposal. So step 2, the expectation of ground motion in real time. So in advance, we need, of course, it's a lot of stations which send real-time data. Network for real-time monitoring of the wave field. This is, of course, necessary. And evaluation of site factor in advance, and evaluation of green function in advance. They are required in advance. And for the real-time analysis, so in this method, the estimation of the spatial distribution of the ground motion is important. So interpolate or extrapolation of the observation to estimate the wave field. This is important. And also the estimation of wave direction, the theta, and also apparent velocities. For example, the array method is useful for the estimation of wave directions and also apparent velocities. Or semblance analysis in real time is one candidate. So estimation of wave front, underground, and also P or S wave recognition may be possible using the array method. And also finally, the application of the idea of Kirchhoff-Fresnel integral. So directly the application of Kirchhoff integral, not necessarily, but the idea of the Kirchhoff-Fresnel integral will be applicable. So anyway, so at the present method is something like that. It's using the observation method and then inverse to the source parameters and then using the source parameter to forward. So, but we know when we observed very well about HEREs, sent information directly to the target. So my proposed method is send information directly to the target. The range we should expect is this range, not for a round trip. Directly information to the target. This is my basic ideas. Okay, so summary, the expectation of ground motion using the real-time monitoring of the wave fields. So, but without hypocentral magnitude. So introducing the concept of time, so near future, for future. Anyway, the idea is looking at the real time from several times before at present, and then using this information, expect several seconds later the wave spatial distribution of ground motions from real-time observation of ground motion directly to future ground motions. So this is my ideas. Thank you very much for your attention.
We have time for a question or two. Yeah, John, can you use the mic?
How much structure do you use in extrapolating the wave field? Do you use the edges of the basins to know where waves might die away or start? Do you use the MOHO to... so do you have to calculate wave propagation, or can you just use a very simple model?
For example, in this case, so I talked about a very simple delta function, but it's an application. For example, it's a stochastic green function, empirical green function, or the empirical green function, the stochastic green function, or sometimes it's some discussion is interferometric coda method. They discuss it's a real green function or not. Anyway, there's some method to estimate the green functions.
Can you also send information on duration of shaking?
Excuse me.
I couldn't get. Repeat, please?
Can you send information on duration of shaking?
Shaking?
Duration.
Duration of shaking is in this case, duration of shaking is not. For example, it's 5 seconds later, 10 seconds later, or 20 seconds later. So we don't expect the durations. So we just the expectation of 5 seconds later, what's happened, 10 seconds later, what's happened. So we don't include the duration in this method.
Okay, thank you.
Thank you very much.
Okay, moving on to the next talk. Next talk is real-time moment tensor inversion and centroid location for large earthquakes for local and regional displacement records. And it'll be by Melgar, Bock, and Krell.
Thanks, Richard. All right, good morning. So we're going to switch gears here a little bit and talk about real-time computation of CMTs. This is work done at Scripps with my colleagues Yehuda Bock and Brandon Kroll. Really, what we're trying to do at Scripps is verify the role or ascertain and quantify the role that real-time GPS plays in rapid earthquake modeling and hazard assessment. And the way we try to do this is either by using GPS data as a standalone product, or by combining it with accelerometer data as well. And I'll wrap around to that at the end. And the ongoing efforts at Scripps are the real-time integration or combination of GPS and seismic data. Earthquake early warning algorithms, of course, where do these data products fit into current earthquake early warning algorithms? Scaling relationships, rapid CMT determinations, rapid slip inversions, and really the end goal of these two products is rapid tsunami forward modeling, where the idea is you compute a CMT, you compute a rapid slip inversion, and you can possibly quantify the intensity of tsunami. Today I'm going to be focusing on this guy right here. And I'd like to show this is the current state of affairs in Western North America. Gray are current existing real-time GPS stations. You can see there are quite a few. And what we're working on now is what we call the next generation geodetic station, where we see high added value in having strong motion accelerometers co-located with GPS sensors. So not just using both data sets, but having them directly on top of each other. Shown here in red are traditional epicenter type force balance accelerometers that are co-located with GPS stations. And in blue, a proposed project to use low-cost MEMS accelerometers and mount them on board with current existing GPS equipment. The motivation, well, this slide is probably moot for this audience because we all know where this comes from, but determining the nature of rupture during the first seconds to minutes of a large event is hard, and doing it with little or no a priori assumptions about the source is harder still. Of course, rapid determination of these source parameters, as we know, is critical for early warning and fast response. And currently, it's done only with seismological instrumentation and can take minutes to hours for these very large events. So we've heard about this very ominously named integration problem. Why is it hard to move from a strong motion record from acceleration to displacement? And the answer is there are many reasons. Perhaps the biggest one is that seismometers can't tell a rotation from a translation. So when strong shaking occurs, as well as being translated, the seismometer is rotated, and the masses will register this motion and interpret it as translation. And this introduces spurious baseline offsets into the acceleration record, which when you doubly integrate, make the displacement waveform blow up, which is why, of course, you'd like to use GPS. This slide, from what I see, is maybe now a little bit outdated, but the point it serves is exactly the same, and is that for the Tohoku Oki earthquake, it took a few minutes to ascertain the truly large extent of rupture. 20 minutes with a W-phase teleseismic inversion, that was the first solution that actually grasped the true magnitude of this event. And of course, knowing that a magnitude 9 event has occurred and that it is close to the trench is critical for tsunami early warning and recognizing the breadth of the emergency. And this slide further motivates that these are maximum tsunami amplitude arrival times at several tide gauges, 34 minutes, an hour and 4 minutes. These are not first arrivals, but maximum peak amplitudes, 29 minutes, 35 minutes. So if we can ascertain the focal mechanism of the earthquake in a couple of minutes, then we have plenty of time to issue a warning. So the way we propose to do this, just a quick peek under the hood of what we call the fast CMT algorithm, is we extract co-seismic Green's functions from Fortran 77 code, EDGRN. This is an open source code. We use a 1D flat layer velocity structure, harvest the Green's functions from EDGRN, which starts from closed form solutions of the equation of motion, and then uses a propagator matrix approach. And then EDCMP computes surface displacements. We don't use this for the inversion, but it's useful during the debugging stage. The way we do this is we need a very coarse preliminary epicentral location. This can be off by 50 or 60 kilometers and it's not a problem. It just has to be somewhere close to the actual rupture. We load pre-computed Green's functions. As most of you know, it is not feasible to compute Green's functions in real time, assuming, of course, some velocity model for the region of interest. And then we weigh the data, the displacement data, with a standard deviation of 60 seconds of pre-event noise to determine which waveforms are more trustworthy than others. We also add a second weighing by 1 over r squared, the distance to the inversion node, so as to not let the stations closer to the rupture overwhelm the inversion. Because GPS is sometimes noisy, we set stations with horizontal offsets smaller than 1.5 centimeters. We set those to 0. And then we invert at every epoch, at every single time step, 1 hertz with GPS data. We can do either an L1 norm or an L2 norm. We find that the L1 norm does a little bit better, of course, because it ignores outliers. So we use this inversion to obtain 5 components of the moment tensor, just a deviatoric solution. And the trick is we combine this formal inversion with a grid searching approach where we invert on thousands of nodes and then determine that the node with a minimum misfit or the largest variance reduction is the winner, and he gets to be the centroid. So this is what that looks like. This is a snapshot of an inversion for Takachi-Oki. These are the inversion nodes. These are spaced, I believe, 0.1 degrees in Latin lon and 2 kilometers in depth. So the inversion is carried every second on every single one of these nodes. And you can see that for at 100 seconds for this particular snapshot, the centroid is located here. That's the point of largest variance reduction. And the beach wall is very similar to the post-processed global CMT solution. Now, how do we actually extract the co-seismic offsets from the data? Because now we have 1 hertz data. So we also have the shaking. It seems like we're going backwards a little bit and trying to ignore the dynamic component and just use the static component. But the way we do this is a simple moving average, where of course we have a trade-off between the length of the moving average window, shown here at 40 seconds, here the raw time series. The longer you wait on that moving average window, the easier it is to discern the static offset, but you lose a critical time. So it seems like about 40 to 50 seconds from our recent investigations is adequate. We did this for Takachi-Oki earthquake before we determined exactly how long that moving average window was supposed to be. In this case, we're being very conservative. This is a 120-second moving average window. Keep in mind that this can be shorter, but for proof of concept purposes, this was good enough. And this is what the data looks like, the GeoNet GPS data for the Takachi-Oki event, and its 3 components. So this is the input into the inversion, and this is what that inversion looks like. Remember, we're inverting each second, and these are the inversion nodes. It's just a rectangular grid. And you can see that at about 120 seconds, we have a fairly good solution. The magnitude's close, the focal mechanism's close to what it should be. And the solution is relatively stable throughout the inversion period. Here I'm just showing 300 seconds. So here's the summary of that inversion, the centroid location, and the focal parameters of the two nodal planes compared to post-process solutions, the global CMT in this case. The size of the CLVD is really small throughout, and the magnitude is well determined at around 120 seconds. We did the same thing for the El Mayor Cucapa earthquake. We have good data, GPS data in Southern California. And of course, the earthquake is smaller, so the vertical components are smaller. You can see one of the troubling things about working with a GPS is that the vertical channel is very noisy, but we can fix that. But anyway, so when we do the inversion for the El Mayor Cucapa earthquake, this is what that inversion looks like. These are snapshots every 50 seconds at 100, 150, all the way to 250. By 100 seconds, the GPS-derived focal mechanism is not very similar to the W-phase real-time solution. But by 150 seconds, the focal mechanism derived from GPS is very similar to the W-phase solution. It's right on this aftershock cloud. It's not at the same position as the real-time W-phase solution, but it's still on the aftershock cloud. And as I'll argue in a couple of slides, I think the GPS is a better solution in this case than the W-phase real-time solution. This is that inversion summary. Magnitude is well determined at around 120, 140 seconds again. We favor a much shallower rupture. And note, please, that the second nodal plane, the strike is fairly stable for the second nodal plane, but the dip for the second nodal plane shows some scatter. This is not a big problem because, as it turns out, this first nodal plane is the one that lines up with the aftershock cloud. The CLVD is very large for this inversion, an average of 0.25 for the duration of the inversion period. Okay, but we can do these inversions, but how do we know when to stop? When do we have a final solution? So the way we decided to do this is we compute the trailing variance of the station with the largest horizontal offset, shown here in blue, Takachioki and El Mayor. We compute the variance of 20 seconds previous to the current epoch, and that's shown in green. And we determined that when the variance is reduced to 90%, this is time t1, when that happens, the final offset is in place and we're done. That will be the final solution. As you saw from the inversion summary, there's still some scatter in the epoch-to-epoch inversions, so we do a little bit more averaging, and we average over the next 20 seconds after this 90% variance is reduced. And what those final solutions look like are here. We produce these little event reports. This is the GPS solution. This is a global CMT solution. They're very similar. Some differences. The nodal plane is 220 degrees for the GPS solution, 250 for the global CMT solution. This seems to agree a little bit better with slab models in the area. And also, we have almost pure thrust, while the global CMT solution has 45 degrees of dip-slip motion, strike-slip motion. They're probably not there. Also, our CLVD is smaller, and we obtain the solution at 211 seconds after origin time. Same thing for El Mayor. The nodal planes are very similar between the two W-phase and the GPS solution. Perhaps the biggest difference is that we have a 64% CLVD, while the W-phase solution is only a 10% CLVD. However, comparing with Eagle-Hawkson's post-processed or post-mortem W-phase solutions, it seems like the large CLVD of 50 to 70% is required and is a real signal given the complexity of faulting here. So we can pick that up with the GPS data, but it wasn't picked up in this particular iteration of the real-time W-phase. And we obtained this at 3 minutes after origin time. Now, just to wrap up, the next step is to combine the accelerometer data directly into the GPS data. And we've shown that this is possible with a real-time Kalman filter that was published in this month's BSSA. And this reduces the detection thresholds or the displacements that we can reliably measure, reduces them to the millimeter order. And this, of course, improves overall data products and the actual time series. I don't have time to go into the details of the Kalman filter, but we combine 1 Hertz GPS data and 100 Hertz accelerometer data and input at the rate of the accelerometer. So what comes out of this Kalman filter in real time are 100 Hertz displacements and velocities. And of course, no talk is complete without talking about Tohoku. And this is real-time GPS data is not easy to come by for this earthquake, but this is an example of the closest station to the source. In blue is the actual GPS observations, and the dots are the actual GPS observations, and blue is the observed Kalman filter. And you can see that the Kalman filter reduces the noise level in the observations. And what you can do with this, of course, is you compute the CMTs, and you can use the CMTs as the nodal planes as input into slip inversions. This is from Brandon's work, and he shows that when you use the nodal plane computed from the GPS CMT, you obtain a much better slip inversion than from assuming a given fault plane. And also, you don't have to assume a fault plane. So if the earthquake happens on a previously unknown fault, like Northridge did, you can get the geometry from the CMT. And also from the Kalman filter, you don't only get the extent of shaking, but because the sensitivity is so greatly increased, you can even see P waves. This is a vertical displacement record from the Kalman filter, and you can even see these tiny, smaller than the millimeter level P waves. So really from the Kalman filter, combining GPS and accelerometers, you recover the whole range of motion. And these are my conclusions. I'll leave those up there for you. But I just want to wrap up by saying that it was really refreshing to listen to Thorn Lay's talk during the Gutenberg lecture, because he echoes what Yehuda and the pioneers of real-time GPS have been saying for years, that GPS serves a very palpable purpose in solving the outstanding problems of real-time seismology. Thank you.
Okay, we have time for one question, perhaps. Yeah, Peggy.
So if you combine the GPS with the inexpensive accelerometers, what do you expect to be the smallest earthquake for which you can do this analysis?
I think the answer to that is not what the smallest earthquake is that you can look at, but what the smallest displacement is that you can look at. So it'll depend on, of course, the size of the earthquake, but how close your station is to a particular earthquake. But as you see from these combinations, which are with high-end accelerometers, we're getting to the sub-millimeter level, really. So even if we can get to a couple of millimeters with these inexpensive MEMS accelerometers, which get better and better by the week almost, I'll be happy. Really, GPS is a strong motion instrument. It will never replace broadband observatory-grade seismometers. It's meant for strong motion. Tom Heaton says 3 millimeters. All right, thanks.
Thank you. Okay, the next talk is applicability of MWP for broadband seismographs located close to the epicenter for the March 2011 Tohoku earthquake. Barry Hirschhorn, Weinstein, and Tsubo.
This thing works from here, huh? Okay. Hi, I'm from the Pacific Tsunami Warning Center. I don't know that this talk is on earthquake early warning, so, but we are talking about response, basically knowing as much as we can about the minimum size of an earthquake so that we can issue a tsunami warning and clear the coasts. So our analysis doesn't have to be particularly fine-tuned. We need to clear a threshold, basically, both in terms of the size of the event and the mechanism. Is this the one that changes the... Okay. This is the derivation of, this is essentially where the MWP method comes from. Seiji Suboi in 1995 basically made a number of assumptions in the equation for the far field displacement from a double couple point source. And when you boil that down to something that we can run as a proxy, you end up with the moment of the P wave from the maximum of the absolute value of the integrated displacement, which in this case should be a proxy for a pseudo time function. Okay, I emphasize pseudo, but very effective. We don't account for the focal mechanism because we don't necessarily know what it's going to be a priori, and again, we want to do something very, very quickly at the minimum possible level to save as many coastal residents as possible, which means a quick warning. So what Seiji did was he compensated for, I guess, a priority for the focal mechanism by just averaging over the focal sphere. So this is the RMS of the focal, of the radiation pattern, and then this is the number you would get, which you would have to which would translate to adding 0.2 to the moment magnitude. And what we do is we wait until we've got the event's moment magnitude, and then we just add that constant to it. And then finally we add this. In 2002, it was sort of independently recognized by our warning center, the Alaska Tsunami Warning Center, and NEIC at USGS that there was this systematic, it wasn't a one-to-one if you were to compare this with the global CMTs, the GCMT MWs. So we fudged it, and we basically, using a data set of 150 some odd earthquakes spanning a large magnitude range and slightly overlapping sets from different organizations, the three of us, we come up with essentially the same regression coefficients for the slope and offset against the Harvard MW, and we just apply this to all subsequent data. So the data that I'm showing you is all subsequent data to that derivation. So here's the first shot plot of what you have here is MWP against the Harvard GCM, what used to be the Harvard number, but now the GCMT. And the black dots are using STS-1 broadband seismometers only. The red dots are everything else. And so we've crudely divided the data set up into those responses that go out to 100 to 360 seconds before falling off, and maybe those at more like 50, 60, in case of the STS-2, 120 seconds. So it's clear there's an improvement of 2 or 3 magnitude units, 0.2 to 0.3 magnitude units as we get to the larger events, which you might expect with the longer period content of the larger events. But I guess the take-home point is that we're actually seeing that difference. So it does make a difference. So here we actually have the STS-1. So from now on, I'm talking about STS-1s. And these are the STS-1 results. Again, everything since the regression set. And the blue line is just the one-to-one agreement. For the most part, we're doing pretty well. The most notable outliers are, of course, Sumatra, which I don't think we had a chance at. And then this is the 2001 Peru event in June of 2001, and it was a complex event with two releases of energy, something like 60 or 70 seconds apart, with the larger release actually taking place in the second event. So we're essentially catching the first moment release with that underestimation. Here we have the distance. This is essentially individual observations with distance of MWP right out to, I think that's 100 degrees. And of course, since they're individual observations, there's a lot more scatter than you saw in the event averages I just showed. But I think the take home here is that within this scatter, you can't say that from this information anyway, that it's doing any worse within 5 degrees than at any other distance. So here's an example of using this extremely closely to a magnitude 6.7 earthquake, which occurred in Hawaii. And you can see that, well, this instrument isn't an STS-1. It's, I think it's a Gorob with a fall off of somewhere around 50 or 60 seconds from the flat response. But even for an event, getting up in about the 6.7 range, at 77 kilometers, we did pretty well. What this is the gray here, which you can hardly see, is the broadband velocity seismogram. The blue is the integrated displacement, or our proxy for the moment, essentially as a function of time. The S wave is coming in here, and the green is essentially applying translating that to magnitude, MW, at each sample point. So magnitude, if you will, is a function of time. And so the maximum of the moment rate would then correspond to the magnitude that we used, which was 6.5 in this case, at 77 kilometers from the epicenter. At 100 kilometers from the epicenter, we got similar results. And so we were able to go out for this event within 3 minutes or so with an event that wasn't quite, but was approaching our threshold for issuing a warning. Actually, incidentally, I got to be there is one relationship to earthquake early warning here. I got to be a human earthquake early warner because being on Oahu, I was 50 seconds away, P-wave travel time, and I had our initial call to the civil defense out, and then I felt the shaking. So I guess we are relevant to earthquake early warning in this slightly. This is an example where basically we also have individual measurements, not average measurements, and now I'm zooming in. These yellow clouds are just for comparison purposes. Those are measurements taken at all epicentral distances out to, close to 100 kilometers for these same events. And the red ones are just those observations that were made within 5 degrees. So essentially up somewhere in this 7.5 area, I mean, there's a lot of scatter, of course. But then from somewhere up into about the 7.5 range, we seem to be at least tracking MW. And there may be something happening up here in the larger sizes in this, where we're falling off for larger events, possibly because we're essentially in the near field at that point, or the near field contribution is big at that point, relatively large at that point. So I guess the next step in all of this was Seiji was able to obtain 18 STS-1 seismograms from the FNet from NID in Japan. And these, here's the epicenter, again, just the epicenter, and these basically span 2 to 15 degrees. And we wanted to see, if we looked at this with distance, what can we dig out of this for useful information that would both exceed our threshold for getting something quickly to the populations, but perhaps not get quite to the final magnitude of the earthquake. And in addition, where would we get? At what distance would we start to see the true size of the event? So these are those same stations arrayed by distance. So now you got 2 degrees up here out to 15. By the time you get to about 10 degrees, we're using a 120-second window for this analysis. So the S comes in before that at less than 10 degrees, essentially. So anyway, you can see the P waves, at least, even in close, are not clipped. So we have useful information there. So here, what I've done is, now you're looking at integrated displacement, or a proxy for moment rate. And I've cut these windows at the S arrival times, and I was very careful about that because it makes a huge difference for obvious reasons. And depending on what you use, I was conservative in my estimates of the S minus P times. So they're chopped maybe a little bit earlier in some cases as opposed to later. And what you see is, you can see this first pulse in the moment rate is, where we're catching this, and somewhere at about the 8 to 10 degree, I would argue that we begin to see something that we can actually use as the final, that gives you a final magnitude for the earthquake. So here are those same results with magnitude for each of those, for the peaks of each of those first integrated displacements with distance. The blue line is at the final magnitude of the earthquake, and you can see even here, varying from 2 to something like 8 degrees, I guess, with this one guy jumping up. At least we're in the 7.7 to 8.4 range from that first bump in the moment rate function. And since our threshold for issuing a tsunami warning, an urgent one for the people who usually get killed, the highest casualty rates are people in close to the earthquake, for obvious reasons. And we would have what we need to get them off the coast here. So we should be able to do something very quickly from this, within a 2 to 3 minute range. And then at about 10 degrees, it looks like we do, if you believe 3 data points at this point, or 4, at least we begin to see the true size of the event. So again, I want to emphasize that since, we're not after a particularly refined result, we're after something that will give us reliable, fast information of some estimate of the size of the earthquake, some minimum size, so we can clear the beaches, clear the coasts. These are our criteria at the Tsunami Warning Center. So from 7.6 to 7.8, we would issue an urgent regional tsunami warning for people, the coastal residents, within 1,000 kilometers of the epicenter. And if we can do that in 2 to 3 minutes, we have what we need, I think, fairly early on, even for these very large events. So in summary, MWP is providing accurate estimates of MW from seismometers within 5 degrees epicentral distance for earthquakes up to about 7.5 to 8 within a few minutes of origin time. Again, based on STS-1s, which have the broadest, which have the widest long period response. For the MW9 Tohoku earthquake, MWP can estimate MW values of 9.1 to 9.3, beginning at about 10 degrees epicentral distance, and at that point, if you account for the 120-second window and the travel time of the P wave, without the latency issues, you're probably at around 4 minutes of origin time at that point. In many of these cases, because of the shallow water and the shallow bathymetry near the coast, there are delays in the tsunami travel time, so it can be as much as 15 minutes to a half an hour before the tsunami arrives at the coast. So this should give a usable amount of warning to coastal residents. PTWC issues tsunami warnings for earthquakes greater than 6.8 in the Hawaiian waters in Hawaii, and for earthquakes greater than 7.5 elsewhere in the Pacific. So we're well above that threshold based on these results. And to hammer a dead horse again, the MWP values of 7.7 to 8.4 obtained at 2 to 9 degrees epicentral distance exceed our threshold, and also most criteria used worldwide, I think, for issuing tsunami warnings in the closer residents, the near field residents. So that's it.
We have time for a question or two. John.
Are you planning to use GPS data soon in tsunami warnings?
We are planning to use it. I don't know about soon. Yeah, no, it's a good question. I mean, it's critical. And
Can you repeat the question?
oh, repeat the question. I'm sorry. The question was, are we planning on using GPS data and soon, or not? And the answer is yes and no. We absolutely are planning on using it, but I really don't know how much progress we've made at this point of actually incorporating it. I mean, we're sort of waiting, we're sort of keeping track with everybody and staying in touch, and as we see things sort of, morph into something that becomes more and more usable in terms of some of the processing delays and stuff, we do plan on using it.
Couldn't we have more dart buoys than we have? We have a lot of GPS and a lot of seismometers and a lot of broadband, but couldn't they also run all the way from the trench to the coastline on plate boundaries?
Well, the dart buoys, that's an interesting question. The dart buoys aren't really intended for warning the near coast to where the dart buoys are situated. The dart buoys give you a deep ocean measurement of the waves independent of all the near surface effects. It's linear in the open ocean instead of getting all the complex effects of nonlinearities near the coasts in shallow water. So those aren't really, the darts are actually placed between the trench, the causative trench, and the more distant targets. They really won't, they're not really, I would argue they're not really intended for the coast closest where the dart buoy is. So I think the plan is just to do our best to cover with redundant dart buoys the areas outboard, out towards the sea from the trench, in front of any potentially, any potential megathrust or worse, slow quake.
Okay, thank you.
Thanks.
Okay, thanks, Barry. The last talk of this morning is the first session this morning is insight into the rupture process of a rare tsunami earthquake from near-field high-rate GPS at McPherson Hill, El Sluicy, Barangi, and C.
It's a PDF, yes.
We don't have a drive.
Okay. Hopefully on the full screen. Good morning. And if I click, it advances. Okay. Hello, I'm Ken McPherson. I've been studying the rupture process of a tsunami earthquake. I'm not sure how much this talk has to do with earthquake early warning, but with this particular event, I think there are some lessons to be learned, and hopefully it's applicable. Let's see what happens when I push this. Okay, that's good. So I've been looking at the October 25th, 2010 Mentawai earthquake. This event fits a description of what Kanamori and others have described as a tsunami earthquake. These events are characterized by low rupture velocities, very shallow slip, and of course their most salient feature is that they produce tsunamis that are out of proportion with their moment magnitude. So this particular event had a moment magnitude of about 7.8, but it produced tsunami run-ups locally in excess of 6 meters with maximum run-up of over 16 meters. Unfortunately, this event killed over 500 people in the Mentawai Islands. Just to orient you, the Mentawai earthquake ruptured a portion of the Sumatran megathrust up dip from a great earthquake rupture in 2007 event. The rupture patch is shown here. And so Mentawai ruptured up dip from that. And actually, this rupture patch that I've shown here is really kind of out of date. And we now prefer an even shallower rupture near the trench. And in fact, it seems like the rupture patch for Mentawai didn't actually intersect the 2007 rupture patch. But we're very fortunate in the Sumatran margin in that we have these islands along the forearc high that are excellent platforms for instrumentation. And consequently, this event was recorded by the Sumatran High-Rate GPS Array, or SUGAR. And the recordings produced by SUGAR for this event are really pretty spectacular. So when you first glance at these, you just think, wow, these are seismograms. But if you look closely, these are, of course, high-rate 1 hertz GPS recordings, and they captured a full displacement history. So you can see the static offset followed by the Rayleigh wave arrivals. So really a beautiful data set to work with. And so just a word about tsunami warning. With an area that's so well instrumented, a reasonable question might be, well, could we have triggered a tsunami warning for this event? And it seems like maybe not. And the reason is, even though we have this proximal, dense, high-rate GPS network, the rupture was so far up dip that the static displacements were actually quite small for this event and may not have triggered a warning. Also, unfortunately, the ground motions in the Mentawai Islands were quite subdued for this event. Eyewitnesses described the ground motions as slow. And there are some problems with translation, but this seemed to mean that there was a long rupture duration and that the motions were quite long period and quite subdued. And people in this region, of course, understand the relationship between severe ground motions and tsunamis, but the ground motions were not severe enough to trigger an evacuation. So unfortunately, the first warning that most people had that there was an impending tsunami was actually the sound of the wave approaching. So given that low rupture velocities are a feature of tsunami earthquakes, I was interested in trying to model the rupture velocity of this event. And if we look at snapshots of the displacement field, we see here, it seems like we should be able to do that. There's definitely information here about the kinematics of the rupture. So these are snapshots of the horizontal displacement. Okay, so to do that, we decided to forward model this event and input different rupture velocities and just see which one causes the best fit of the synthetics to the observations. So the wave propagation code we use is WPP from Lawrence Livermore National Laboratory. They very kindly make this software open source and available for download. It's a second order, a finite difference scheme for parallel computers. And the inputs into this code, we just use Crust 2.0 interpolated for the velocity model. We use a grid spacing that allows us to accurately model waves of periods down to 40 seconds. And for the simulate the source, the finite source, we just use several hundred point sources located in a plane of the correct orientation. So a bit more about the source model. The slip model is derived from Hill et al. That's a paper currently in press. And this was derived by inverting the static displacements from the sugar recordings of this event, and also incorporating prior slip constraints from tsunami modeling. And notice it's dominated by this very large disparity that's very far up dip, very shallow rupture. And so what we did is we ran a suite of simulations, and for each one we kept all the input parameters the same, with the exception of the rupture velocity, which we varied to try and get an idea or an estimate of the correct rupture velocity. And so I'll show you outputs from station BSAT and also station SLBU. Oh, sorry, it's not marked. This is the output from station SLBU. The east-west component is on the left and the north-south on the right. Data is in black, and the colored curves here are the synthetic output for different rupture velocities. So here in brown is a rupture velocity of 3 kilometers per second, and then the slowest rupture velocity modeled was 1 kilometer per second here in red. And just by inspection, it seems that the rupture velocity in blue of 1.5 kilometers per second seems to fit about the best. And we see similar results for station BSAT. Once again, the rupture velocity of 1.5 kilometers per second in blue seems to be about the best fit to the data. So just some conclusions from this. I think from this forward modeling, we prefer a rupture velocity of around 1.5 kilometers per second to 2 kilometers per second. And this agrees with some previous work. I think maybe I pushed the wrong button. For example, Lay et al. 2011 preferred a rupture velocity of 1.5 kilometers per second based on inversion of teleseismic data and R1 source time functions. And so I think we can use this technique to provide a rough estimate of rupture velocity, but really to get a more robust estimate, I think we need to move towards inverting the full high-rate GPS waveform, incorporating both the static and the dynamic information that's in that data. And some acknowledgments, again, thanks to Lawrence Livermore for kindly making their code available and open source. And also these simulations were run on the University of Kentucky's high-performance computing network. And with that, I'll take questions. Thank you.
We have time for a couple of questions. Okay, well, in that case, that brings us to the... Oh, there is a question. I'm sorry, I can't... It's very difficult to see anything under these lights.
It's just hard to get here. Have a slow velocity. I'll ask the last question again because from a public safety perspective, all the people in these plate boundary earthquakes are dying from the tsunami and not from the ground shaking. if there were, I was thinking if you go to the doctor, he actually listens to your heart. They can do an EKG and all the other testing and do your blood work, but it would seem to me that if you had a dart buoy on the ocean side of that trench where the water was deeper, you would get an early signal. And if you had buoys from the trench to the island, you would be alerted to whether it was a false alarm or not. Is that unreasonable to actually be measuring what's happening in the ocean?
I think so, but unfortunately with this event, most of the casualties were very near source. And also the Mentawai Islands are very remote. And I think getting a message to people, an alert, is just logistically challenging. One thing, they're very near source, so time is limited. And also just the isolation of some of these communities, it's hard to get the alerts to them. And usually what we tell the locals is, you know, be aware of the environment, and if there are ground motions, then you need to evacuate. And unfortunately with this event, there was such a dearth of high-frequency energy that was released that the ground motions were very subdued, and so it didn't trigger an alert. So I think with the Mentawai region in particular is very challenging, and I think while I think a dart buoy, you know, can definitely tell us something, but the logistics of getting the message to these isolated communities is the real bottleneck. Thank you.
Great. That brings us to the conclusion of this first session this morning. We'll be back here in about 15 minutes. The second session we'll be hearing about the summary of current status of early warning efforts in the US, in Europe, in Turkey, in Italy, and also a mobile early warning system in New Zealand. So please come back. See you in about 15 minutes.